Hey guys, this is Fred from Pretty Fly Games, and today we're going to continue with our top-down car controller built in Unity. Today we're going to go through how you can record ghost data and play it back in Unity, so that you can make replays and other interesting gameplay elements in your racing game. So let's go through the theory behind it first. So there are many ways that you can do ghost car replays, but we're going to do it in the same way as you do animations. So what we have is our car here that is driving along the road, and each of these green boxes is a keyframe. And on the keyframe we are storing the position, rotation and scale of the car. So when it's passing through, we can see that the time is now 1, and then we are storing these elements, and then when it reaches time 2 we store it again. So that way we will have a path that the car is traveling through at certain intervals. We are storing the position, rotation and scale. And the reason why we are storing the scale is we want to have the ability for the car to jump, and we want to store that in our animation. So if we look at our time here, it's 0, then we are storing the position. And when we want to play it back, we don't want it to be at just time 0 and then jump to time 1 and time 2. That will make it look very laggy, and for us to compensate for that we would need to record a lot of keyframes, and that will take up a lot of storage and data. So what we do is we interpolate. So even though we have one data stored here with the information about the position, rotation and scale, and we have the other data set here. So what we're doing is we're interpolating in between. So as time passes by, we can see that the car is slowly rotating towards the next keyframe, and when it's on that keyframe it is actually matching up. So this is the method that we will be using when we are implementing this. And what you need to consider is that this is an interpolation, which means that as the car is going through the different, or is between the keyframes, then the data may not be accurate. So if you have are recording very slowly, not as often, then it means that you will have more inaccurate data, so the playback will be less accurate, but it will also take less space when you store it. So the best thing is to find the best mix for your game, so that you're recording the keyframes at a certain interval and then playing them back. And we will use a sort of a naive version of this, but it works fairly well for our types of games. But of course there's a lot of optimization you can do later on. So let's jump back into Unity and go through how to implement this. So for this we're going to use our jump scene that we created earlier, because it has a lot of jumps and nice things that we can use when recording our ghost car. And we will need a new script, and it's time to get a little bit more organized, because we're starting to get a lot of scripts in our folder here. So let's start by cleaning it up a little bit, and we'll create a new folder and we'll call it ghost car. And the first script that we will need in this is a data item. So we need to record all of these frames that I said before as the car is moving through. So let's start with the data item that we will use for this. So we will need a new script called ghost car data list item, and let's open that in Visual Studio. Now in Visual Studio we have our ghost car data list item, which derives from mono behavior. And the first thing we want to do is mark this as a serializable. So it means that we can store the data, and we will be storing it as JSON data. And by adding this tag, Unity will know that, okay, this whole class is going to be serializable. So it means that it can handle the conversion of data and store the data. So the second part we want to do is we want to already optimize our save data a little bit. So instead of having it derived from mono behavior, we will use something called serialization callback receiver. And this gives us the ability to control the data serialization and deserialization a bit more. So what we will have is we will have a couple of data points that we talked about before, and we're going to mark this as non-serialized. That means that when we are saving the data, Unity will be ignoring these parts. So all of this information will not be stored in our data file. So why we're doing this is because we're going to take our position, which is a vector2, and we're going to save the data here. But a vector2 consists of floats. And if we'll take this as an example, this is a float value that is representing something which is very close to 0 as a value. So what happens is if we have a lot of these type of data where we are storing a lot of precision, then it means that the file that we're storing this to will be very, very large. And for our game, it doesn't really make that much difference if it's on 0.1 or if we have a precision of these many decimals. So we will use this to take away some of these problems by reducing how many decimals we are storing. So that's why we are saying that, okay, this data is not going to be saved. It's a vector2 position. And then we have a rotation of the car. That's not going to be saved either. It's a float. And then we have our time since level loaded. And that's not going to be a float either. So to reduce the size, what we will do is we will change these into integers. So we will say that, okay, we have a value x, and that's an integer. And we serialize this. And then we have another integer, that's our y, and that's going to be as well a serialized field, so we're going to store this. And then we have our rotation, and that's also going to be integer. And then we have our time, and that's also going to be an integer. And then we actually have one more field, which is the scale. And that is going to be an integer as well. So what we have now is we have these fields, and we need to tell Unity how to handle them when we are serializing. So as we are not deriving from monad behavior, we don't have any start or update methods, and we don't need them either. So what we have is that, okay, when we are serializing, when we are storing the data, then we will do it in a certain way, and that is a function that is called, or a method that needs to be called on before serialize. And as we see, there's a complaint here that we have not implemented on after deserialize, so we will need to do that as well. So let's add that on deserialize. Okay, so now we got rid of our errors. There are no complaints now about that. And also the error that was marked up here is now gone. So on before serialize, so when we are serializing the data, what we want to do is we want to take our position and take it from vector2 and convert it into the sort of x position and y position as integers. And we want to do that by still maintaining some level of data. So what we will do is we will multiply our values. There are probably several ways of doing this, but this is how I do it, and it's a simplified version. So we take our sort of time since level loaded, which is a float value, and we multiply it with 1000, and that gives us an integer that gives us a precision of 2 decimals accuracy when we are doing this math operation. So we are multiplying it with 1000. And when we are deserializing it again, then we need to do the reverse. So what we will do then is we will take our time and divide it by 1000. So when we are creating the data, we're multiplying it by 1000, and when we are sort of reading back the data, we are dividing it by 1000. So that will give us the ability to have an accuracy of 2 decimal points, which is nice for us, without the data becoming too large. So let's do that with the other variables as well. So on the deserialize, we need to do our position divided by 1000 and etc. And then we have our local scale that is giving an error. So let's have a look at that in a little bit. But before we do that, let's also do our rotation. And the rotation doesn't even need any decimals, so we can just keep and store it as an integer. And then let's store the local scale and rotation on the or everything else when we are storing it. So before serialize. And then we don't have a local scale, so let's see, I probably missed to add that before. Yeah, we need to have that as a non-serialized field, and we will add it after the time. Okay, so great. Now we don't have any errors, and I hope that that was not too complicated, and we'll go through how to use this. And also, actually, when I think of it, right now we have our public variables up here, which is fine. It's easy to access them and it's easy to set them. But we want to create sort of a method to make it easier. So we're going to make a constructor. So a constructor is a function that is called when we are creating this data. So let's just call it, it needs to have the same name as our class. Then the compiler will understand that, yeah, this is our constructor. And in it, we will feed a couple of variables. So we will feed a vector to position, a rotation, the local scale, and also the time since level loaded. So, and we will just store them as our global variables. So when we are feeding in position underscore, we're storing it as position. Okay, so let's save that and go back into Unity. Then we will need another script, and we will call it ghost car data. So this will be the script that is holding all the information and is also holding a list of all of these data items. So let's open that in Visual Studio. So our ghost data, we want to make this class into a serializable object as well. So let's mark it as serializable because we want to store it later on. And let's get rid of the start methods and update, and it doesn't have to be a mono behavior, so we can get rid of that as well. Okay, so then we have our first information that we want to store, and that's going to be our serializable field. And we want to have a list of our ghost car data list item, and we will call it ghost car recorder list, and it will be a new list. So this is where all the data is stored for the position, scale, and time, etc. Then in this example, we're going to make it very simple. But if you, in your game, when you're implementing this, you probably want to store more information, like what type of car are you recording, what color does it have, and all of the other attributes that you need later on to play back the information. So in this case, we are going to skip that to just keep it very simple. And but it's very easy for you to extend this. So then what we want is we want to have as well a way of adding data into our list here. So we will add a function, and we will call it add data item, and it will take in a ghost car data list item. And it will take this list and add the data item to the list. And then when we are playing it back, we want to have a way of getting hold of this list because it's not a public variable. So let's implement a get data list, which returns our data list here. And we just give it a return. Okay, so that's all we need for our data structure. And as I said before, you can extend this on your own. So let's store that and go back into Unity. So with these two classes, we are now ready to create our car recorder. So let's make a new script and we'll call it Ghost Car Recorder. And then let's open it in Visual Studio. So the first thing we need to do is get rid of the update function because we won't be using that. And then we need a new variable, a public variable, a transform, which is the car sprite. So we need to take in the car sprite that we are going to record. And then we also need a local variable for our ghost car data that we created before. So let's start that up. And then we need some way of determining if we are recording or not. So we will add a bool variable for that, is recording, and it's going to start as true. And then when we are recording, we also need access to the car's rigid body, and also we can use another thing. We'll come into that later, but let's start with the rigid body. So let's get a rigid body, car rigid body 2D, and we will use our awake function to fetch that, as we have done before with the get component. So then we have access to that, and then we want to record at certain intervals. And the easiest way to do this is to use a coroutine. So we will use a coroutine that we call record car position CO. I like to use the word CO just to show that it's a coroutine. And in a coroutine, we will need a yield return, and because otherwise it's going to show an error. And the yield return basically executes all the code above here, and then it waits for this given period of time before it continues. So we want this to be running all the time while we're recording. So let's add a while loop around that. So then it will enter the while loop, and it will execute the code we have here, then wait for this period, and then run again. Okay, and what we want to do is while we are recording, we want to add these keyframes that we talked about before. And we can have a simple check before and make sure that we actually have our car sprite object, because if we don't, then there's nothing to record. And then we'll use our ghost data, and we'll use our function add data item, and that function took in our ghost car data list item. So then we need to create that. So let's make a new ghost car data list item, and that takes in position, rotation, local scale, and time since level loaded. So let's feed that into our function. So we'll take the position from the car rigid body position and the rotation from the car rigid body as well. But the sprite is the one that we are scaling. So that's why we needed a reference to the car sprite, as we had, as this is what we are scaling when we are jumping and things like that. And then we'll add the time since level load, and then we can close that. Okay, so this function also needs to be started, and we use a start coroutine with the function's name, or the complete name as shown here. You can also use it as a string, but I recommend that you do it this way, because then you can feed in parameters easier into functions. So if we are running this now, then every 0.15 seconds it will record a new keyframe, and it will add it to our data item list. And what we want to do at some point is that either when the sort of car has finished the race or when a certain thing happens, we want to store this keyframe. And we want to store it in some type of file system. And So, but in this tutorial, we will keep it super simple, and we will use Unity's built-in system for this. So what we'll do is we have our save data function here, and we will encode it as a JSON. So we will create a string, JSON encoded data, and then we use this beautiful utility called JSON utility, and then there's a function called toJSON, and we can just call it with our ghost data class. So that will create a JSON encoded file with all the information in here. And that's all what we need to do to get this data into JSON. So it's really simple. And what we can do is we can output it just so we can look at it in the console later on. And we output it by using debug.log with the data. And then we want to be able to store this information, and we will use, as I said before, the player prefs to do it, because then we don't have to worry about the file handling. You can change this into recording into the file system or whatever you want, but we will use the player prefs for it. And but to make it a little bit more efficient and interesting, we will use a few more things in this so that we are recording the data per scene and also per player. So for it to work, we need to include a few more things. Let's start by using the Unity scene management, so we can get access to what scene we are currently playing. And then we want to be able to access the car input handler, because that tells us which player is this. And we need to get a reference to it in our awake function. Okay, perfect. So now that we want to save, we can check that for sure that we actually have a car input handler, so we don't by mistake attach this to our AI, for instance, which doesn't have the car input handler. So that way we know that it's an actual player. And then we will use player prefs, and we will use set string, and we can feed our JSON string right into this, and it uses a key. So the first thing is a key, and then there is some data. Our key name here is what we will use to make sure that we can reference it into each scene, etc. So we will replace this with scene management get scene, and then we'll take the name from that, and then we'll use an underscore and car input handler dot player number, and then underscore ghost. So that's the key name. And then we will feed our JSON encoded data straight into that. And then we need data to close our string as well. All right, and then the only thing we need to do to save the data is to use playerprefs.save. Now this section here can be replaced by any type of file saving, but for this type, playerprefs works fairly well. It works on most platforms, and yeah, it's quite handy. So now that we have stored our data, we can also tell our recorder to, yeah, we're done with this. We don't need to record anything more. So normally you would call this when a car finishes the race, but to make it a little bit faster when we are testing, we can add another coroutine for this. So let's add a coroutine, and we will call it save car position CO, which just waits for 5 seconds and then saves the data. So we need to start that as well in our start function. Like that. And now when we are starting, it will start to record the car's position, and then after 5 seconds it will save the car position CO. So let's save that and take it for a spin in Unity. So in Unity, let's select our car, and I have created a prefab from this earlier, so I'll open the prefab. But if you don't have a prefab, you can just create it right or add it right to the car's object. Then we'll drag in our ghost car recorder, and we need to assign the sprite object. So let's go and add that. That's the car sprites in my case. And then we can exit and take it for a spin. So if we run around here for a few seconds, we can see that, okay, the console has now saved that information. And we can see that this is how it looks like. So we have our ghost car recorder list, and this is the first part of the JSON. And it has this X value and a Y value and the rotation, time, and then our scale. And this is the one entry, and then after 0.15 seconds, this is the next entry, and then it goes on like that for, well, the entire part of the race. So what we need to do now is we need to create a new class to be able to use our recording now that we have that. So we need a new script for that. So let's create C# script, and we'll call it ghost car playback, and let's open that in Visual Studio. So the first thing we're going to do is we're going to add a variable, and we want to be using our ghost car data. So let's create a variable for that. And then we also want to have a list of our ghost car data, so the information that we have for each keyframe. And then we want to load this from our player prefs that we had before. And we also want to make sure that when we're loading data, that we're loading it for the right player number. So let's have that as a variable, and we'll make it into a public function because we want to be able to access it from other functions. So the first thing that we can do is we can check if we actually have some recording. If we don't, we need to add scene management as well. So let's add that using scene management. So what we do here is we check that if we do not have a key that is called scene management and with the scene name and the plane number and ghost, then it means that we don't have a recording for this. And this playback script will run on its own object, so it will be its own little car that is playing back the information. But if we don't have any recording at all, then we can get rid of it, because then there is no point in having it in the scene, so we can destroy the game object. But if we do have this key, then it means that we actually have the data. So let's decode our data, or get it out of our JSON. So first we need to load our JSON encoded data, and we'll use our player prefs, and we'll use the scene management, active scene name, player number, and ghost as information. And then the JSON data will be loaded here. What we do then is we do the reverse to get the information out. So we will use the JSON utility from JSON, and then we just include what type of class it should be when it's read the information. So it's going to be a ghost car data, and from this data. So out of this, we actually get our class back with all the information pre-filled. So super simple, super easy. And then when we have read it, we want to access our data list. So let's do that by adding our ghost car data list, and we are using our function that we created before, get data list. So then we have access to that information here. Perfect. So now that we have loaded it, we can actually start to play it back. And what we do is we will go through all of the keyframes in the list. So the first thing we need to know is then what part, what index, what keyframe are we at? So we will use a variable for that called current playback index, and it will start at 0. So what we will do is in our update function, we will start to read this data. And the first thing we need to check is that, is there any data? If there is no data in it, then we can return. And it could happen if the update function has been called before we have actually had time to load the data. So if that happens, we are just checking that, yeah, we're not doing anything until we actually have the data. And then what we want to do is we want to move the frames forward after a certain time has passed. So we will match that up with the keyframe, the time that we have stored. So what we do is that we check that, okay, if the time since level loaded is larger or equal than the time we have for our keyframe, then we should do something. And what we will do in this case is that we will move it forward when we are done with the processing, and we will make sure that it's staying within the bounds of the data. So what we will do is we will step to the next item, but before that we need to check that we have not gone sort of beyond the list. So we make sure that we are not going above it before we are increasing the index. Okay, so if we run this now, it will just step through the index and nothing will happen. So what we need to do is we need to move the car, this object, forward. And we need a few variables for it. So let's go ahead and create all of those. So we need the last stored time, we need our last stored position, and our last stored rotation, and our last stored local scale. And these will be used to interpolate the next position. So when a new frame is starting, we will take all of these variables that we had. Last stored time will be accessed from the car data list with the current playback index with that time, same with the position and everything else. And then we need to create a new variable called duration. So the duration will show, okay, how far have we gotten in our data frame. So we need to calculate how much time is it between our actual time and this ghost car time. So what we do is that we take our duration will be the time since level loaded minus last stored time. That's the duration of this sort of short clip that we have. Okay, so now that we have that information, we can start to move the car. And we will do that with a lerp function. And a lerp is moving between 0 and 1. So we need to get it into a percentage form. To do that, we need to calculate, okay, how much time has passed. So we will calculate it by using time since level loader minus the last stored time. And we need to have this to figure out, okay, how much percentage should we lerp. So what we will do is we'll take create a new variable, lerp percentage, and we'll take time passed divided by duration. Then we will get how much percentage we should lerp. Now that we know this, we can start to lerp. So we will start with the position. So we'll take the transform's position and we will use our vector2.lerp with the last stored position and the position we want it to be in with the percentage. So this will cause it to smoothly move from the last position into this, and it will look smooth even though the data is periodically recorded. And then we need to do the same thing for our rotation, and we have the same function on the quaternion. We have a lerp there, and we lerp our Cotillion Euler from the Z rotation position, the last store rotation, into the current rotation that we have in the keyframe. And then the last part is that we want to do the same thing for the current scale, so or local scale. So let's do that as well. So let's add that for our local scale, and we do a vector3 lerp from the last stored scale into our current local scale with a lerp percentage. Okay, so that was some things to take in, but it's not that tricky after all. So just have a look through this, and it should be working for you in every scenario where you want to lerp things. So let's store this, and we will need to create some new things in Unity. So let's get back into Unity. So now we need to create our ghost car playback object. So let's take our car, and we can duplicate it, and then we will unpack it. So select unpack prefab completely, and then we can rename it to ghost car playback, and then we can get rid of the shadow and the canvas and everything, and we can get rid of the outline and all of the scripts and rigid body and everything around it. So let's get rid of all of these things. And then we will drag our ghost car playback script into it, and then let's create a new prefab out of this. So beautiful. Now we have our little prefab, and to make it a little bit more easier to handle, we will actually delete it from the scene view and just keep it here. Now in our car, we can go and let's open our ghost car recorder again, because we will make it a little bit more clever, so it actually also spawns the ghost playback object. So let's open that in Visual Studio. So in our script here, let's add another public variable. So we'll take in a game object, and it will be the prefab that we just created, the ghost car playback prefab. And when we are reaching our start function, then we will create a copy of that. So let's instantiate it. So we instantiate our ghost car playback prefab, and we'll keep a reference to it as ghost car. And then we want to instruct it, okay, we want to load our data. So we will do it sort of a little bit of a dirty way. We'll use a ghost car get component, and then ghost car playback, load data, and we tell it that, okay, this is our player number, because we get it from our car input handler. And if there is no data, our ghost car object here is self-sufficient, so it will destroy itself if it doesn't exist. Okay, so let's save and go back into Unity. So in Unity, let's open our car prefab again, and then we need to assign our ghost car playback object that we created before. So let's drag that in, and we'll go back, and if we press play, it should now load our ghost car data and create a sort of a version of that. So there we saw it, it created it. It looks absolutely the same, which is not that great. So let's go in and change that again. So we'll open our ghost car playback object, and what we want is this car. We want it to be a little bit more ghosty. So let's reduce the alpha so it becomes transparent, and then we can take it for another spin. Now it will actually just stand still because I didn't drive that much before. So let's make a new recording. So now we saw in the console that it saved the data. So let's take it for a spin again, and then it should be a lot more moving. So now we have our ghost car system, and it also works for sort of a single player game, or if you want to record a multiplayer game. Now what you need to do is, as I said before, The ghost car will be just the red object now. If you wanted to have different colors or different car types, etc., you need to enhance the system with the information. But now you have the basis to do that on your own. So I really hope that you enjoyed this video, and please give it a thumbs up if you did, and also hit the subscribe button if you want to get a notification when the next video is out. I'd also like to give a special thanks to all of our Patreon supporters, and especially MSGS Europe, that has reached the wow level in our benefits on Patreon. The link to our Patreon page is in the description below, so please consider supporting us there. Here's an example from our game, Total Arcade Racing, which uses this component for its physics, inputs and other parts. You can find the game on Steam, Xbox and Nintendo Switch. Please take it for a spin if you want.